Um, let's see. So hi. So I thought I'd go through the quiz. I think everyone did pretty well on the quiz. This was a molecule we did before. The earlier quiz had this Tylenol. And so, but this is an ethanol. That was the only difference. That changed the phase behavior a little bit. You basically had to go through the so you had to use the activity coefficient calculator web page using Unifac liquid-liquid equilibria, put in the right parameters for ethanol and paracetamol, and then search out the that's the wrong thing. This one. Search out the infinite dilution for well, just to follow these things. So infinite dilution for paracetamol gives you X1 alpha, and then infinite dilution for ethanol gives you the X2 beta. And then you find out the other one minus that gives you the other component, and then you plug those values into the activity coefficient calculator, the compositions, and then you get the activities. So you can plug those in here, and then from the activities, you can calculate the Ks from the beta to the ratio of the beta to the alpha for like 2 and 1 gives you the Ks. And then once you have the Ks, it's 1 minus K. Let's see. Let's see here. X1 beta is 1 minus K1 over K2 minus K1, and then X2 beta is 1 minus X1, and then X1 alpha is K1 times X1 beta, and then X2 alpha is 1 minus, and they just do the same thing. So you plug those numbers into activity coefficient, get the gammas, and then repeat until you do 5 times and you get the composition. So that's the compositions here after 5 iterations. And then once you have those, use the phase diagram so to figure out what these A by F and B by F. I think almost everyone got these. Let's see, there's a sketch of it. So you have the alpha and beta, and then you're feeding at 55%. So the amount, so the beta by feed is going to be alpha, F minus alpha divided by beta minus alpha. And then the alpha is going to be 1 minus that. So that's these two. And then the moles, paracetamol and beta is the beta, the amount of 1 mole going in that goes to beta, and then the fraction in beta, that's paracetamol, which is 0.372. So those two times each other gives a 546. And then a couple people weren't able to do this, the melting point calculation. That was, you guess the temperature. So you guess some temperature, and then that temperature will give you gamma through the this activity coefficient calculator. So you put in the temperature that you want, and that gives you the gamma if you put in the composition. So say the beta composition and then temperature gives you the gammas. And then when you have the gammas, once you have the gammas, you can calculate the melting point using the using the melting point equation, which is in the quiz, I guess. It's in here. It's like this equation. So once you have the gamma and x, you can calculate t. You have Tm also. And then that t, the t you get there, you plug back in to the gamma calculation, get a new gamma. And then with the new gamma, you calculate a new t, and you just do that back and forth until it doesn't change anymore. So I don't know, somehow a couple people weren't able to do that, but mostly everyone could do it. So there's a lot of 90s for the quiz. I think everyone seemed okay with it. Oh, then the plot, like a lot of people will ask points here on how to plot them. So you have the composition here. You just got these two temperatures. You can get more if you want. Like I did 0.1 and 0.25 to see kind of where this thing goes. So basically, you plot that composition and that temperature. People didn't seem to get that. Like they weren't able to make those plots. Lost 5 points for not being able to do that. But it's 100% paracetamol. That's the paracetamol melting point, and then just drops. So you end up with this big gap, right? There's a huge temperature jump, like 100 degrees. So it's kind of likely that even at the feed, I mean, there's a big driving force for crystallization, probably more than for phase separation. So even the feed probably would crystallize before you ever phase separated beta. And that could be a problem. And then the rate of crystallization is really high for this stuff. So I don't know. So there could be problems with the process here. You could mention those, or you just say it was okay. That's what I said. So that's online. Any questions on the quiz from anybody? So anyway, I think everyone did really well on it. You know, it's kind of not that easy to do, but people seem to pick it up, so that was good. Anyway, so I want to do, so we got 2 weeks left, kind of 1.5 weeks, but since we don't do Thursday, we really have 2 weeks, right? So I thought I want to do chapter 17, which is reaction, equilibria, and then I wanted to do chapter 18, which I haven't put into the thing here yet, but it's electrolytes. It's like strong acids, strong bases, weak acids, weak bases, batteries. What else is electrolytes? It's useful. It's similar. It carries on from the reaction thermo, and it's stuff that it seems like from looking at the companies where you guys work that it's pretty important, like sulfuric acid and different concentration regimes for it, and you know, basically everyone's going to be using like caustic and HCl, and so I think that basically the electrolytes is a pretty important part that you should get. So getting a kind of a jump into that is useful. This so 17 is equilibrium for reactions. We already in chapter 3 we already did some kind of equilibrium. We didn't do equilibrium, but we did kind of the basic reaction stuff in chapter 3 at the end of chapter 3. So we did first we did the stoichiometry for the mass balance, right, with the reaction coordinate, which you maybe already saw before this. So in this case, like you're given the reaction coordinate and then you just calculate what comes out of the reaction. So we did that already. You may or may not remember it. And then so you can figure out the compositions from using this reaction coordinate idea. So hopefully you can kind of remember that a little bit. And then we calculated the energy. So in this case, you're given the reaction coordinate. So it's like, says something like you're given the conversion of something. 5 moles, 2 moles combined in a da-da-da-da, develop an expression from mole. So just develop the mole fraction if you know, given the reaction coordinate. And then we did some energy balance on this. So the energy balance ended up giving this weird expression for the heat of reaction, right? And then this is a 298-degree 1 atmosphere heat of reaction. Then you add in the heat capacity change for the reactants. These delta A, delta B, delta A's, the stoichiometric coefficient times the activity times the A components. These are the A, B, C, D for the heat capacity from the back of the book, from table E in the back of the book. Anyway, we did that. And then you end up with this J, and to solve the J, you do the 298 heat of reaction. So you put 298 for the temperature, and you say that delta H0T is delta H0R. So you have this value tabulated, or you calculate this value from the news. So you sum up your components times each of the heat of formation, so you get the delta H0, and then you throw in T is 298, and you get this J parameter from the heat capacity numbers. And then once you have J, then you solve at any temperature what the heat of reaction is. So basically solving this involves this J constant that you figure out by doing the 298. So we'll use that. We need this thing. We need this thing in this chapter because we're going to be figuring out the equilibrium constant at different temperatures. And then we did if you remember, we did the heat of reaction method and the heat of formation method. 2 methods to get the delta H, which ended up being essentially the same math, right? So that's what we did back in chapter 3 for reaction. So we didn't do, we didn't get the equilibria. Like what about calculating the equilibrium constant? So here you're kind of given the extent of reaction. In chapter 17, you calculate the extent of reaction using the equilibrium constant, this Ka. So for an ideal gas, the equilibrium constant is going to be this. It's going to be the reactants and the ratio of the reactants and the products. You probably remember this from chemistry. Let's see. Seems to be working. Expand this thing. All right, so that pi means you have Ka, like if you have A plus B goes to C, then you have the products. So you have like kind of YA P. So if it's like 2, then it's YA squared, P squared plus, not plus, YB P, and then C, YC P. Right, so the P cancels and you end up with P squared. So you have, this is for ideal gas, YA squared, YB, and then one over P squared is Ka. Right, so those are the news. So nu is 1 here and 1 there. It's this number. And then that's kind of how you get Ka, the reaction coordinate for ideal gas. Right, saying that the activity is Y times P. So this Y times P is actually the activity, chemical activity, which is also going to be the fugacity of the I component divided by the fugacity at 0 of the equilibrium of the pure component of I 0, whatever. This is pure. This is in the mixture. But this caret means in the mixture. So that's kind of where this chapter is. So calculating the equilibrium constants, like the main part of this chapter. What's the temperature change of the equilibrium constant? If you have a vapor and a liquid in equilibria during the reaction, so one of your products is a liquid or a solid, how does K change? Those kind of issues are what's important in this. So first off, there's this issue straight off. So there's a book, I put a book up of that has to do with reaction engineering, like how, or this book's on the web page. So it's this thing, fundamentals of chemical reactions. You might want to look at this. This guy Davis. So Mark Davis is a pretty famous catalyst guy at Caltech. He's like one of the biggest people in catalysis. And then he has a brother, I guess, Robert Davis. They wrote this book together. Robert Davis is at Virginia Polytech. So they're the famous one's the first guy, Mark Davis. So he's like kind of like Mr. Catalysis. So you can, like, basically what we're going to go through is more or less like chapters 1, 2, 3. Like this is our chapter 17. And in this book, the chapters are really short. Like a chapter here is almost like a section in our book, a section of a chapter. So the gas phase reaction is a pretty simple part of this thing. And then it gets more complicated when you look at heterogeneous reactions. Now, so we're only, of 1, 2, 3, we're only looking at the equilibria. So there's two parts to the whole operation. So you're going to have, so this is kind of a reaction coordinate, basically means it's not extended reaction, it's just something like progression of the reaction, like the reaction's done here, and then the reaction's not started here, and then here it's going on, right? And this is energy. So the idea is like we can, with equilibria constant, this Ka, we're going to get like between A plus B and S plus W, what's the energy change? And that tells you, so if it goes up, it's exergonic. So that's called exergonic. And that's bad or no. And it's argonic. So argonic means energy. So it's consuming energy, or N is N. Let's see, exergonic is good. Sorry, X means it's giving off energy, and endergonic is bad. Means it's not going to go. Like the reaction won't go. So if you have this case where your reaction has a higher energy at the end, that means you have to put energy in to make the product. So that's not spontaneous, right? Whereas if your energy drops, that's spontaneous. So it's exergonic, gives off energy. Exergonic is usually also exothermic, like it's also going to give off heat, right? So, so this could be gasoline, for instance. Like gasoline is exergonic. There's a big energy change, right? It's huge energy change, but it can sit in your tank without doing that, right? So why is that? That's because there's a barrier energy. So in order to get gasoline to reach its fruition of giving off a huge amount of energy, you have to put in energy to get over this barrier, right? So there's a barrier energy and activation energy. Once you activate it, boom, it explodes, right? But before you activate it, it won't explode. So the activation is you put in a spark, right? That's some kind of energy you have to add to it. And then once you get over that, it goes. You've probably seen this before. So this is a Arrhenius behavior, right? An Arrhenius, so you'd expect that the rate of reaction would go with, so log of the rate of the reaction is going to be like the energy, the activation energy over KT, right? So that's an Arrhenius. So you'd plot log of rate versus 1 over T, and then the slope would be the energy. And if it could be either a positive exergonic or a negative energy endergonic, right? So that would be kind of the scheme of things here. So we're not interested in this at all in this course because we're not doing rates. We're just saying, like, what is the start and the finish, right? What's the equilibrium of this thing? Like once you reach equilibrium, have you given up energy or taken up energy or given out energy, right? So we're only interested in the beginning and end of these things. That said, the equations for the two things almost look identical. right? So you're going to have this reaction constant is going to be, yeah, it's going to be the Y's and the P's the way I showed here, right? So it's going to be like the products divided by the reactants and raised to the stoichiometric powers. And then if they're gases, it's going to be with the P to the power for each of the parts. Depending on how many, it would be P to that power, right? So that's basically for ideal gases, this YP thing. And then, but if you're looking at the rate of the reaction, like gasoline, you could have a huge Ka, right? So you're going to get like 46. So this G, delta G is going to be 46 megajoules per kilogram for gasoline. It's a huge number. That's why you use it to drive your car around. It's a huge amount of energy. Megajoules, right? It's a huge amount. So if you compare that with a lithium-ion battery, it's 0.46 megajoule per kilogram. So it's 100 times less energy in a lithium-ion battery per kilogram compared to gasoline. Right, so that's a big barrier to get over. Like if you want to drive an electric car, this is a big problem, right? Also, you can fill this thing up pretty fast, and to fill up the battery takes time. It takes a little bit of time. And there's been improvements in that, but still a factor of 100 is a huge thing. It's mitigated a little bit because the car engine is 50% efficient and the electric motor is almost 100% efficient. So it's really 23, still 50 times more, right? So it's still a hurdle to get over. That's why electric cars are going to weigh a lot. Like the Tesla is like the same, it's like a ton and a half or something. And it's a sports car, like a Model 3. Right, it weighs a lot, literally weighs a ton. Whereas if you took a, I don't know, a Jaguar sports car, it's not going to weigh anything like that, right? So anyway, that's kind of the issues with this. You know, these kind of issues come up about the kind of the energy of a reaction, right? So gasoline thermodynamically is totally not stable, right? But kinetically, it's stable. In other words, you can have a tank of gas and leave it in your garage or your lawnmower, not worry about it blowing up. Unless someone happens to go smoke and a spark gets in, then you get over that energy barrier and then you release this thermodynamic instability, right? It's totally released and get that huge amount of energy. Anyway, so the rate constant, again, it's going to follow an Arrhenius behavior. It looks almost exactly the same as this equilibrium constant. So this is the equilibrium energy change. So we had the enthalpy change. We had delta H in chapter 3, right? So we had chapter 3, we got this delta H heat of reaction, right? And then we need here not delta H, but delta G. We need delta G, right? So you can use the Gibbs-Helmholtz equation to get that delta G if you know delta H. So we know how to get delta H reaction. Then the change in delta G by RT dt is going to be delta H over T squared over RT squared. Right? We had this Helmholtz equation before. So we can get delta G if we have that delta H from chapter 3, which had that J thing in it. So we can calculate what delta G is as a function of temperature using the Gibbs-Helmholtz equation, which we developed at some point. It doesn't matter, but basically it's possible to get delta G from delta H, and we have delta H from chapter 3. So we'll get delta G, we'll get a similar expression. So we can calculate the equilibrium constant at different temperatures. This reaction rate constant looks like almost the same thing, but it's related to this barrier energy idea. So there's a barrier you have to go through to get the reaction to go. How fast the reaction goes depends on the temperature and how big is that barrier, right? So that barrier is this activation energy over RT gives you the rate constant, and there's two rates involved. One's a forward rate going forward and one's a backward rate going backwards, right? So you have those two rates, and then the difference in those rates gives you the total rate. It's either going to go forward or backward. It's going to be how those relative those two are. If it's an ideal gas and there's nothing special happening, then these are the molar concentrations, and so these are concentrations like gram per volume, and then or moles per volume, right? And then that can be raised. So M could be A and N could be B if this is an ideal situation. And the only thing that's happening is that the gas atoms are flying around. So you have A's and B's, and you're just looking for the collision. Like, do they collide? Once they collide, they react. Right. So that's kind of an idealized situation. Right. So that's basically an ideal gas kind of model. Like they collide, they react. That's not how things usually or often happen. Sometimes you need to have like two A's and one B to react. Like 1 and 1 doesn't work, right? Or there's some other relationship that they have to have. Like they have to say, if it's a heterogeneous catalyst, you have a chunk of something, then an A has to bond to that heterogeneous catalytic site, and the B has to pull in, maybe 3 B's have to pull in a certain arrangement, and then it will release the product like AB. Right. So any kind of weird thing like that happens, then these numbers, these powers change. So you can have different orders of reaction. Whereas in the equilibrium constant, these are always like the stoichiometric numbers, right? Because you're just talking about before and after. You don't care about how it happened. You don't care about these details. You just care about what's the energy of that final product compared to the energy of the initial things. What's the change in energy? And that gives you how many miles do you get from a gallon of gasoline, right? The energy that you can get out of it. Right, so the two questions of like how fast does it react and what energy do you get out of it are two different questions, right? What energy do you get out of it at equilibrium is another part of this. So this might not react to completion. So you might not get to the complete equilibrium concentration because you don't have time to get there. So you might end up halfway to the equilibrium. Right, so this equilibrium balance is basically a hypothetical equilibrium that possibly could happen. So it tells you the direction things are going to go. It doesn't tell you how fast they'll happen. Right. So anyway, so that's kind of the idea of this. Arrhenius, I mentioned before, he also predicted in 1896 that we'd have global warming, and it was discussed in public then before 1900. Right, it was extensively discussed in public, like global warming was going to happen. Despite that, that was completely ignored until about 2000. Right, so Arrhenius invented this equation, but he also made some other things that he did. He's a Swedish, I think, scientist. But anyway, that rate theory was later popularized by Irene and some other people. Right, Irene was a guy in the U.S. at Cornell, so it's called the Irene rate law sometimes. Anyway, so these two things look the same. We're interested in only the equilibrium here. If you go to this, book, it includes both. It's going to talk about equilibrium, and it's also going to talk about the kinetics, meaning like the reaction rate constants. And then when you get into the kinetics, you have to talk about these catalytic sites, like heterogeneous catalysis is going to be things like, how does this reaction site look? So it's worth kind of glancing at the future. You'll go through this in one of the classes, reaction engineering. So it's worth kind of glancing at this stuff because it's actually more interesting, I think, because it's really closer to like what governs the reactors and things that you're dealing with. The equilibrium is important, but basically in the end, you care about how much stuff did you make, and then how the catalyst structure kind of impacts that. So these are typical heterogeneous catalysts, like what you'd see inside a catalytic converter in a car or in a chemical plant. These go into a bead column or something. So you have a packed column with these particles in it. And these are kind of nano size. This is 25 nanometer. These are small transition metals. And on the surface of those transition metals, you can see the crystallinity, then your reaction happens. So it's not going to be a gas phase, ideal gas reaction. So this reaction constants are going to be, or the reaction orders are going to be different. Like the powers here are the order of reaction. Anyway, so that's that business. So, so if you're given this equilibrium constant, so say it's a small number, that means reaction is probably not going to go, right? So this is for conversion of carbon monoxide to methanol using hydrogen, right? And gives the stoichiometric ratio of the feed and the temperature and the pressure. So here you're going, so if the number of moles on each side are the same, then the pressure doesn't matter, right? But here you're going from 2 moles, 3 moles to 1. So the pressure will drive this reaction. The higher the pressure, so they're going to 20 bar to get this reaction to drive to the right, right? So the pressure will shift this reaction. The reaction constant stays the same, right? Because it's going to include the pressure in it for the calculation. So that will impact the mole fraction, but the constant stays the same. So it's not, constant isn't affected by pressure. It'll be affected by temperature. So we'll figure out the temperature dependence, right? The pressure you calculate when you calculate the mole fraction. It's mole fraction times pressure. If you assume ideal gas, here everything's gas. So you assume ideal gas because it's at high temperature and because it's easier. Right? So anyway, so you have Ka, and then you can just, that's the expression for Ka. That's the ratio of the products of methanol divided by the reactants. So negative power. So it's divided by, there's 1 CO and 2 H2. So the H2 times pressure is raised to the power 2, and producing 1 methanol to the power 1. Right. So you have P, the P's cancel, you just end up with 1 P out of this. The product has 1 and there's 3, but you end up with 2 P's. So the reactants have 3. So you end up with the power 2 of P squared here. And then the Y's, well, the Y's you don't know yet. Right. So how do you get the Y's? Chapter 3, we figured out how to get the Y's. Right. In order to get the Y's, you have a reaction coordinate. So you don't just say, and just say like 2 moles and 1 mole, because you have a 2-to-1 ratio. You have to figure out what that'll, because that changes as the reaction proceeds, right? Depending on the extent of the reaction, the moles change. So at the beginning of the reaction, it's 2 and 1, but then at the end, it's going to have some methanol. I mean, it would be 0 methanol, and then this would just be 0, right? So it wouldn't work to take the moles, these moles, because those moles change constantly through the reaction. But no, at the end of the reaction, what was the extent of reaction, and that'll give you the moles. Right, so the CO starts 2 minus the extent. Hydrogen starts 1 minus the reacts 2, so it's 1 minus 2, and it's going to produce 1 methanol. So the limits on these, which we also went through in chapter 3, so you can't go negative in any of these. That's kind of the rule. So you have, this thing could be a half, right? If this is a half, then hydrogen goes to 0. You've consumed all the hydrogen. So the maximum it could be is a half. And then the smallest it can be, since you're making methanol, that can't go negative because you can't have a depletion of methanol. Then that can go at least, least it can be a 0. So you have no reaction, or you can have a reaction coordinate of 0.5, and you can't have anything other than that. Right? So anyway, you have these limits, and then you can express the mole fraction. So CO2 minus reaction coordinate divided by the total moles gives the mole fraction. And you can do that for each of them, and you can plug those back into your equation for the reaction rate constant, get that. Then you can calculate an expression. Let's see, so the P has been put into this 232 because the P is fixed. So you have the pressure fixed, so you put the P into that constant, and then you can just solve this by trial and error. So you put this into Excel, use solver, and it'll spit out 0.21 for the reaction coordinate. So it's up 0.21, that's between 0 and 0.5, so that's good. Then if you want to know the extent of reaction in terms of CO, you take the original 2 moles of CO. So 0.21 divided by 2 moles gives 10% conversion of CO. And if you do it in terms of hydrogen, you started with 1 mole. So it's consuming 2. So it's 2 times 0.21 divided by 1 gives 42% conversion in terms of hydrogen. So the conversion is going to depend on which species you want to use for the conversion. Right. So this stuff is mostly from 3, with the exception, chapter 3, with the exception of there's a rate constant here to do the calculations with. So most of this chapter is how to figure out what that rate constant is. Right. I mean, you can also look at, so the chapter also looks at like driving the reaction. So like in other words, the pressure was high, you could change the pressure that would drive the reaction. The higher the pressure for that case, the higher the reaction. So this is picking up on from chapter 3, where we had the H thing, right? We had this business of calculating the heat of reaction with this J constant. So we have a heat of reaction. We know how to get it using the heat capacity, right, for each of the components, and then the J thing. So how do you relate that to this Gibbs energy reaction that you need to get the rate constant, right? Because the rate constant is going to be exponential. So log of the rate constant is the Gibbs free energy change. So the Gibbs free energy change is the exponential of the Gibbs free energy change by RT is going to be the rate constant. Right, so we need the Gibbs free energy change to get the rate constant. In other words, the products minus the reactants. That's what I mean by the change. So Gibbs from the square, thermodynamic square is S dt v dp. And then if it's so the reaction is going to run at constant temperature and pressure, hopefully. Right, then we can drop these two terms. And then it's just the chemical potential. So this is the extrinsic. So this is the actual value of Gibbs, not the Gibbs per mole. Right, so this is the value of Gibbs. It's going to be chemical potential times the moles change. Chemical potential is the change in Gibbs with respect to moles of that component. So that times the change in that component's moles gives you the Gibbs, the actual value. Right? If you want the G without the underline, you have to multiply the total number of moles here. Right? So we're using this because this thing uses the chemical potential directly. Right? So this is for the reaction. So if this is for a given state, but if we're talking about a reaction, then we want that the number of moles is going to be the extent of reaction. So the change, it's a change in moles, is the change in the extent of reaction times the stoichiometric number times that component's chemical potential, which is also done in chapter 3, right, to get that relationship. So once you have that, and then you can say that at equilibrium, the change in Gibbs is 0. So you can just pull this over and you have dG d extent of reaction is the sum of these chemical potentials times the stoichiometrics. And that has to equal 0. All right, so that's kind of that's just the way how the Gibbs fits in. So so this Gibbs, this is defined as a log of the fugacity ratio, and the fugacity, I mean, this is the fugacity in the mixture of components, and this is a fugacity of the pure. So because this is times here and it goes log, the times goes to a power. So it's a power of the fugacity ratio. Fugacity, not fugacity ratio, the fugacity, whatever this is, between the component and the mixture and the pure. That's the chemical activity. Right. So in other words, if it's an ideal mixture, then this is basically just Y times P activity, right? Or it's X if it's a liquid. So anyway, so that means you're going to have this basically this relationship ln of activity to the nu, or ln of Y times P to the nu, which we already have, and we know that that sum is going to be the K. So this pi times A means a multiplied. And then that's basically the definition of the activity coefficient. So that means that this delta G is exponential of delta G is Ka, or K is the log of K is this summation of G of the components. All right. So anyway, all this leads to the final result that you're going to have almost the same thing that you had from chapter 3. So you have this thing, so we end up with this constant J that has to do with this, the 298 1 atmosphere value for the heat of reaction, and whatever the heat capacity numbers are. And then oops, sorry. And here you have another thing, because you're going to have to use the Gibbs-Helmholtz function to get this relationship. So you're going to have to oops. So this is the standard state, like the one at 298. How do you calculate Ka? So you can look up all these Gs. The Gs are all given in the back of the book, right? They're all in the, I think it's like the first appendix or something. Yeah, it's a G of formation. So you have like E1, G of formation for kind of everything. Liquids, and it goes to ideal gases. We have all the G of formations here. Right, so all you have to do is like look up those numbers for the components of the reaction, and then you get the change in free energy for the reaction. Those are all set at 298, so you can get it at 298. So you can do a problem like, what is the standard state at 298 for the Gibbs energy change? Right, so you just look up those numbers, and then you just plug in the Gibbs. I think you're ignoring the H here, right? So you look up the Gibbs, you plug them in, and then you just calculate, right, what it is. The Gibbs by RT gives you Ka. So you just plug those in, right? So, and then everything is one here. The stoichiometrics are all one, so there's no powers, right? And then that's it. That gives you the Ka at 298, right? So this is using that with let's see, this is just showing, this is something separate. So this is just showing that if you put it, so you have here, like you're going 1 mole to 2 moles. So you're taking butene, which is just like this guy, so 1, 2, 3, 4 carbons, and then you're converting that to this guy, butadiene. So this one is used to make polybutadiene rubber. So that's like tire rubber, or styrene butadiene rubber, SBR. So those like two. So this one, when it polymerizes, it's going to make like this polymer. So it's going to have a double bond in it, and then when you want to make a tire, you react it with sulfur to crosslink. So you get the sulfur attacks a double bond, and then take another one. You can link the polymers together. So butadiene is like a pretty useful industrial chemical. Butene is a product of like refining oil, so you want that conversion to happen. So this is a pretty common conversion. And it uses a catalyst, right? We just mentioned the catalyst. We don't care about the catalyst because you're doing thermodynamics. So we just need the beginning and end. We don't need to worry about the rate. If you want the rate, then you need to think about the catalyst that you use, right? Which is in that other book. So anyway, so it's just fine. Look up on the table the heat of formations for these guys, and then you need to know, this is trying to do this at 900 K, so you need to change the temperature of this guy. But he gives the let's see, he gives the, I think he gives the reaction coordinate, the Ka at he gives the Ka at 900. Like he gives you that value here. Like it's given here, delta G 900. Like he gives it heat of formations at 900. So then you can just add up to get the delta G for it. And H is a ground state, so it's got a zero delta G of formation. In other words, the things that are like O2, H2, nitrogen, N2, argon, those are all 0 for heat of formation. The others have some other heat of formation. So this is just add those up to get delta G at 900. He gives the numbers from 900. That's why you don't need to change the temperature. And he gets the Ka. Once you have the Ka, you do the same thing, except that he's adding in 10 moles of steam, which doesn't participate in the reaction, so it's an inert. right? But because you're making 1 mole to go to 2 moles, so it's going to be like a pressure rise. If you dump in, so if you put it under vacuum, that would help this reaction, right? Or if you put in the moles over on this side, it drives it to the right. So because you have a higher pressure here, it drives it over to the lower pressure, right? So basically adding inerts or pulling a vacuum will make this reaction go faster, right? So he does both of those. He puts in an inert 10 moles, and then he also pulls a vacuum on it and see. So it says, what extent of reaction do I get if I put in 10 moles? It's going to be much higher. Then what is it without the 10 moles? It's going to be much lower. And then put in the pressure to make it match the first one. You find out you have to pull a vacuum to make it shift over because of the way it's set up. Because 1 mole going to 2 moles. So you pull a vacuum, it's going to favor the 2 mole side. Because you're trying to pull off, almost like pull off the products. So so you do that, then the difference, the nuance here is he has this extent of reaction. So he's just got this 10 added in. So the total is higher. So when you divide through, you get a big, smaller number for each of the components. Then you have this equilibrium constant that you got from the some of the G's, and then take exponential minus of that by RT gives the Ka. And then basically you need to just use solver to solve this thing. I mean, you figure out like what's the range possible for this extent of reaction. So so you can't make less than zero, so it has to be bigger than 0, and you can't have bigger than 1 because you get negative here. So basically it's between 1 and 0. So this usually, there's not a simple rule to figure out how to get this range. Like it's kind of by inspection. There's no algorithm to get what that range is. Like you inspect this thing and you figure out what it is. And you could be wrong. So I mean, you have to kind of be careful about it, right? There isn't, so without an algorithm, it's a little bit of an open-ended thing about what that range is. But it's important, that's always determined first, to figure out what the possible range is. So you know your answer is possible or not. Like the answer here for A is 0.784, and the other one I think is 0.44, and they're within that range. That's okay. So 78% conversion when you solve this with Solver in Excel. Solve that last equation. And then if you get rid of the inerts, then this is going to be 1 plus eta. So then you get this equation at the bottom. When you solve that, you find out that it's that you get 44% conversion instead of 78. And then if you put in the 78 and say what pressure is, to change your pressures to solve this equation for pressure. So there's a pressure here because you're making 1 to 2, so there's 1 pressure. Then you can set the pressure to, you can set the extent of reaction at 78, and you find out the pressure is a vacuum, 0.1 bar. So 1 bar is an atmosphere, 0.1 is less than an atmosphere. So you can either pull a vacuum on your reactor and it pulls off the product, kind of drives the reaction, or you can add an inert. So adding the inert is a lot easier than pulling a vacuum, right? So it's much easier to just dump in steam, which is free, and just that'll drive this reaction, right? But then you have to separate steam from the butadiene. But if you condense it, that's not going to be a problem because it's like oil and water, right? So basically condensing this, which you might want to do anyway, will solve your separation problem, and it's going to be a huge advantage to use steam to drive this reaction. Right, it won't be hard to do the separation. This is just, we already talked about this, is energy consuming or energy generating. Then this is the thing about the Gibbs-Helmholtz. So we had in chapter 3 this business. We got the heat of reaction with this J constant. And solving for the J, we just put in 298 for the temperature, and we have this delta H0. That's the 298 number we just calculated from the back of the book, the summation of the delta H's from the back of the book. Then we can get this J. Once you have the J, then we can get delta H at any temperature. Just plug the temperature in. And these delta A's are the sum of the A's from the back of the book, the ABCD for heat capacity. So so we do the same thing for delta G. But the easiest way to do it, since we already have delta H, is to use the Gibbs-Helmholtz, which relates delta G to delta H by 1 over T squared. And you'll remember this thing gives you dt over T squared, which is d1 over T, right? And this thing gives you, so it gives you 1 over T versus exponential of the energy on this side somehow. Because this is delta G divided by delta H, that ends up being 1 over the delta G is delta H minus ST. So basically this ends up being exponential, or this ends up being log, and this ends up being 1 over T. So d log of delta G and d1 over T over here. So this gives you a plot, like an Arrhenius plot, log of the energy versus 1 over T. Versus that the slope of it gives you like the delta H. So that's how we used it someplace when we first got the Gibbs-Helmholtz. Anyway, it's a common function that we just have. It's basically it relates delta G to delta H. When you plug this through, you're trying to solve for Ka, which is going to be exponential of delta G. So basically, it gives you this equation, which looks something like the H equation that we had for chapter 3. Like chapter 3, we had delta H is going to be J plus these deltas from the heat capacity. And this thing's going to be delta G, and it's got that J, the same J in it, right? So to get this J, you have to go back and do the delta H thing to get the J. Right, so you get the Gibbs numbers for delta H, and then add them up to get delta H0 for the reaction. So it's a sequence of events here. Right, so you're gonna have to get the delta H to get the J. Then you plug in 298 to get the J. So you'll say delta H0T is delta H0R when it's 298. So you just put in 298. Then you subtract those two and get J. Then once you have J, then you can go to this delta G number that comes from the Gibbs-Helmholtz. And then you have another problem that you have an integration constant I that came out of it because it's an integral. This thing is an integral. So it ends up with a constant of integration that you need to find. So you find it the same way. You go through your table, delta G is at 298. You say temperature is 298. You have J from this thing, then you get I. This is a fairly tedious process. Then you can get delta G at different temperatures. An exponential of minus delta G over RT is Ka. That gives you the Ka temperature dependence. Okay, so that's messy, so it's just programmed. This is just a sequence of calculations, right? It's programmed in Excel, and it's called KCalc. So actually, we don't need this thing anymore. Quiz 13, don't need the answers. It's this KCalc thing. So it looks pretty simple here. The instructions are here. It's basically like, give me, oh, I shouldn't have clicked that, go forever. But there's some instructions here. But basically, this is it. You look in the back of the book. You find delta H. You find the heat of formation, which is in that table E. Right? You find the heat of formation for your stuff. This is E section. Quite a few things going around here. So this E section, it's got heat of formation 298, and it's got the Gibbs free energy of formation at 298. And it lists it for everything. I mean, there's some blanks there, but basically a lot of things. If not, you can go to the Chem web book at NIST and it'll give those numbers. Right? Just Google Chem web book, and then one of the boxes you check those numbers. So anyway, you put in those numbers, and this A, B, C, D are the heat capacity numbers from the back of the book. Put those in, you put in the temperature you want, and it's going to spit out Ka at the bottom. It'll also give you the delta G at that temperature they typed in. Delta G for the reaction. Right? So this just goes through all those calculations, gives you J, gives you I. It does it all for you. You can look up what the equations are, but doing this by hand is extremely tedious. So usually in the past, we've done it by hand, but basically we just use this KCalc to get it. This will just spit out the numbers. So you don't need to go through that. anyway, so that we had time. So we'll just kind of pick up from here next time. Maybe use this K-calc to go, there's a problem here to, example. Get the constant at some other temperature. Right, use K-calc. So we'll just go through that next time. All right, so again, like we're gonna do 17, finish 17, have a quiz Thursday, then we'll do 18, and then 18 I'll put onto the final. So the final will be like 2 questions. One will be 18, one will be from the other stuff, the other things that we've done. I haven't really looked, like I'm gonna wait until after this quiz, and then I'll let you guys know who doesn't need to take the final. But I imagine it'll be like there'll be like 2 people out of 24. So basically almost everyone's gonna probably have to take the final. Right, so anyway, but it'll work out, I think. Everyone will do okay. It's just like probably mostly everyone's gonna need to take the final. So the final's worth a lot of points too, and it'll be like individual, so it won't be like pairs, so I think it'll work out okay. So anyway, any questions on anything? We're out of time, but okay, so I'll see you tomorrow, 2:30. Yeah, thanks.